actually, I went into my YouTube videos and I looked at the video with the least amount of views, the lowest views on my account that is a regular technical video. This video here is the video with the lowest views and it's still a technical video. I thought that would be fun to watch. Let's figure out why it has so little views. Was it that bad? This is from 2017, so that's 4 years old, and it only has almost 7,000 views. It was a collaboration together with Paul Scher, who is a researcher who found an exploit in FFmpeg. So in the RTMP protocol, a heap buffer overflow found in 2016, actually. I forgot how this worked. There were like two multiple series or something. If you see here, there's like video 1 of 2, and is this 2 of 2? I don't remember myself. Was this a full video? I don't remember. So we're gonna watch it together. We will figure it out. It is just 7 minutes long, so it shouldn't take too long. By the way, there is also a Live Overflow podcast, which has exactly 1 episode from 2017, which I did interview Paul Scher. I was very motivated to make a podcast back then, and then I stopped and I only did this 1 episode. Check it out, I guess. Subscribe to this podcast. I still think it's a great podcast episode. But yeah, let's check it out. Let's see how this video is holding up or not. And maybe I can, with my experience from 2021, say what I would have done differently in this video, or why it was bad or good, or what I like about it, and so forth.
Let's have a look at another FFmpeg vulnerability. Again, Paul will walk us through the vulnerability that he found together with Emil, and I try to understand it and add some comments, hopefully to make it a bit easier to understand.
In the previous issue, we achieved code execution quite easily. This time we will have to be much more accurate during exploitation.
I know, Russian accent, difficult to understand, but when it's a Russian accent, you know it's going to be real. Also, if you don't know, I have subtitles for basically every Live Overflow video. Because I write scripts and so forth, I can also provide subtitles, and these are not auto-generated, or usually shouldn't be auto-generated. It's something only I do for the main channel. So if you have trouble understanding something that I'm saying, try out the subtitles. There are a lot of typos in those subtitles because they're just like quickly written. But yeah, there are still subtitles, I think, which is valuable for people that maybe want to watch a video when they can't listen to it. For example, one person wrote me once, he's watching my videos while he's having his baby sleeping, so he can't listen to it in this moment, and so he's just reading the subtitles.
This crash was found during fuzzing the RTMP protocol. This protocol is binary, so let's open it up in my favorite hex editor called Radar2. I like it to use when viewing the binary files, because it has a very shiny UI.
Okay, so Paul is showing us here the crash binary. So this is a hex dump of a file that contains the proof of concept crash.
Nothing too special here, just some binary data. So let me tell you something about this protocol. RTMP stands for Real-Time Messaging Protocol. Actually, it was developed by ADAP for real-time streaming of audio and video. The protocol has actually a lot of stuff inside it, and I had spent some time learning the specs before getting into the exploitation. All you need to know about the RTMP protocol so far is that it doesn't handshake first, and then it starts to transfer data in small chunks, and maximum size of each chunk is 128 bytes. Now let's dig up into the source code once again. So, after passing the...
So here we are in the so this is FFmpeg. So FFmpeg, if you didn't know, is a tool to convert video files, for example. Is a utility to handle a lot of different file formats and so forth. And parsing file formats can be very buggy, so there are once in a while interesting exploits. And so here it's about RTMP, because FFmpeg can also stream video with RTMP or receive video streams with RTMP. And this is the RTMP packet.c. So this is the packet parsing or packet handling implementation for RTMP inside of FFmpeg.
Version check and doing some handshake to the source code once again. So, after passing the version check and doing some handshake, we end up in the packet read function in RTMP packet.c. This function simply reads one byte of the header and then calls the most important function in a loop. And this is the function which does all the parsing of the protocol. There are a lot of structures, functions, and allocations, and all of them are important. As you can see, each chunk has the channel ID. It is basically identifier of the RTMP packet in the array, which corresponds to its own buffer. One channel may be filled by multiple chunks, because maximum size of each chunk is 128 bytes, and packet data might be much larger. Each chunk has fields like size, type, header, timestamp, and some extra data. So, if the current channel doesn't exist yet, RTMP packet structure is filled in the array and the buffer is created for it. So, the vrlog function with null pointer means simply do the allocation of the corresponding size. Otherwise, data is just filled in the existing structure and the buffer. So, if you will pay enough attention, you may notice the issue there. When the structure is filled for the second time, there is no check that the buffer size is passed for the second time is actually the same, that the size of the allocation made the first time. And this is how we will manage to get the heap overflow.
Okay, so me watching it now again, I also don't understand anything. Okay, I didn't catch why the second time the allocation size is wrong. Here I clearly failed with visualizing it better in terms of pointing out where he's talking about. So yeah, but also I'm jumping in now, so maybe I explain it now again.
Yeah, this makes sense. So the packet contains a channel ID.
Okay, so this is something I do typically with all the interviews and collaboration videos I made, where I re-explain it now in my own words. So hopefully this should be clearer now.
Yeah, this makes sense. So the packet contains a channel ID read from the header. And if this packet was not seen before, it will allocate it with this size. But if an attacker sends the packet with the same packet ID again with a different size, it will not be reallocated. Let's visualize that. If we send a packet with ID and size hex A0, it will get allocated. And then we can send another packet with ID 2 and the size hex 80. It will get allocated after the first one. Now we send again a packet with ID 1 in a much larger size, like hex 200. Now we overflow stuff on the heap. Awesome.
So,
okay, I think now that was actually pretty clear what happened. If it saw a packet with a certain ID before, it just reuses the buffer it already allocated. But when the size changed, it would just think, oh, my buffer is larger, but it was actually a lot smaller allocated. So now this packet just overwrites other stuff on the heap.
how we are going to get the code execution? Overflowing another data chunk does not give us too much. Let's try to gather some primitives from the source code. So we could allocate data chunk by sending new channel ID. We could overflow the chunk next to it by changing the size.
This is also, I should have maybe emphasized this more here. Now you have an overflow, but the question is, what do you overflow now? What can you overflow that gives you anything? This is also the problem that we will soon face with the pseudo series. What do we actually do with the heap overflow? We need to overflow something that leads to some kind of code execution at some point. And so he's now looking for primitives for things he can overflow and use in some interesting way. And so here he's saying, as you've seen in the previous picture, if you receive a packet, it gets allocated. If you receive a second packet, it also gets allocated. So your overflow can overflow this packet now, this data chunk. So he says you could allocate more data chunks and you could overflow them. Maybe these data chunks have interesting fields in the data that could do something. I believe overflow the next chunk is probably the real heap chunk, not just the data, but yeah.
Primitives from the source code. So we could allocate data chunk by sending new channel ID. We could overflow the chunk next to it by changing the size, and we could also trigger the reallocation inside the RTMP check alloc array function. If we send channel ID large enough, we will trigger the reallocation of the control structure, and it will be positioned right after our buffer we can overflow.
Okay, so he found here in the source code a way how he can trigger a reallocation of maybe a linked list or something, or an array, a reallocate array, because there's an array for all the channel IDs, and if you send a channel ID that's too big, that doesn't fit in this array, now it needs to be reallocated to make bigger, and that reallocation obviously puts it somewhere else in memory, and it puts it after the buffer where you have the overflow in. So yeah, so now you can overflow this array structure. So let's see why he likes this array structure. You obviously could now go and look at the type of this array. And if you see the struct or how this array works, maybe there are some interesting fields. Yeah, let's see what he says.
By doing this little heap magic, we overflow the pointer to the data and get arbitrary right.
That's a super easy plan. We just force the reallocation of the array that contains the pointers to the data chunks, and thus the array will...
So did you see that? There's an array that contains pointers to all the chunks. So this is an array, and this so if we go before here, this is the array of all the RTMP packets, and this has a pointer to our first packet data with the ID 1. And now if we send a larger ID packet, it will be reallocated, so it will be allocated after that, and we know that we can overflow everything after this data chunk. So now we have this array, and this, like I said, this array contains pointers to where the data chunks are. So if we overflow this array with the pointers, we can have we can specify the address where, if we then try to write a different ID packet, we write to whatever data to whatever address we have overwritten.
That packet we have. And then we send again a packet with this channel ID to overflow into this array, and thus control the address of those data chunks and can point it anywhere we want, and thus also right there.
So here we overwrote this array with data, and we could control the address, and the next time we send a packet with the same ID, it will check, oh, what is the address of this data chunk, so that I can write data, but now it points somewhere else, and we can overwrite something else. Now we have, now with this primitive, we went from just an overflow into the next buffer to a primitive that allows us to write anything anywhere. Write anything anywhere. That's the exploit primitive. And with that primitive, you could now look for a function pointer to overwrite, and in that step then gain the actual code execution.
So I already did some preparations before and wrote a little proof of concept, because most of the work here was counting offsets. So there are the functions I wrote. These are lambdas for packing our integers using little endian. Create payload function helps me to pack data into the RTMP protocol. And create RTMP packet function will help me to create fake RTMP structure on the heap. Now let's take a look at the main code. So here's the handshake happens. After the handshake, I send first payload with size just a bit bigger than 80 bytes in hex and some A's and the channel ID number 4. I do this to create control structure on the heap. Next I send some data with larger channel ID to trigger the reallocation of the control structure. Next, I overflow the next heap chunk, which happens to be control structure, and fix its size, so I will have no problem with the heap when I will be allocating more data. I position the fake chunk on the place of the RTMP packet with second channel ID. As you can see there, I position the realloc.plt.
So here he got the address of in the global offset table for realloc. So he's overriding in the global offset table the address where the realloc function would be. Usually it points into libc, and so this is the target address he's overriding to, and he will, I don't know, let's see with what he will be overriding it.
Instead of the data pointer, so I will be able to write to it.
What is the difference between reallocation and use after free? Reallocation has nothing to do with exploitation. Reallocation is just you reallocate a buffer. We can talk about this in a moment. And use after free is a vulnerability pattern, an exploit pattern, or a vulnerability pattern. So reallocation simply means, so you have the heap memory. There are these, when you allocate something, you just basically say, okay, here's a piece of memory that you are allowed to use now on the heap, and you have the pointer to it. What realloc does, it just looks where's space on the heap, and finds, oh, here's space that is larger, you can use this, and you get this new pointer. Please, from now on, use this pointer. So realloc is just a way to basically free the previous chunk where you were and reallocate it again as a bigger chunk, you know? So reallocation is just programming. It causes just a reallocation, which is interesting for this heap exploitation technique, because this way you can influence where this array will be in the heap. Because here is your, make my face full screen. So here is the array. Here's the buffer you can overflow. And now you overflow data below it, but that doesn't help you. But he figured out that you can reallocate the array at the top, and reallocating means it will search for a new space on the heap, which happened to be right below our buffer. So it will be reallocated here. And now our buffer that we can overflow is right above it. And now we can overflow into that array. So the reallocation was just a happy accident, or a way to force an object that he liked onto the heap right after the buffer we overflow. There could also be other packets he could send. This was just what he figured out. He saw, oh, he could force this reallocation and get the array after it, which can be turned into this right anywhere, anything. It has, so the vulnerability is the heap overflow, and the reallocation was just used to get an object into the area that is overflown, an object that is interesting in that area that can be overflown. Does that make sense? And use after free is a vulnerability pattern, because it means you allocate memory, you free that memory. Now this pointer should not be used anymore because that object doesn't exist anymore on the heap, but you still use it somewhere else. And when you write other data onto that heap area, and code is still reusing that pointer to that heap chunk and uses the data there, weird things and problematic things can happen. Make heap bigger or smaller. Reallocation necessarily doesn't make the heap bigger or smaller. If you reallocate something so big that it doesn't fit into the current allocated heap chunk, it will extend the heap and create a new heap or so as well. But in reallocation itself is just you allocate some memory and then it's not large enough. So you realloc can be basically write your own realloc algorithm. Realloc could be you allocate a huge area that is now enough space, you copy the old data into the new array, into the new buffer, and now you free the old one. That's a realloc. Yeah, reallocate is just a function here used to allocate again a buffer that is bigger enough. It's just a helper function. And like I said, the helper function does nothing else than allocate a buffer that's large enough, copy the data over from the old buffer, and free the old buffer now because we have reallocated it now. Okay, that's all it does. It's just a helper function. Yeah. And use after free, as I said, is a vulnerability pattern. Does that make sense? Oh, hope this explained it. Let's finish this video.
As my last steps, I write a got.plt with some data, and after I use big channel ID once again to trigger the realloc function. All this should give us control of the RIP register.
So yeah, he overrode. So he wrote to the array of data buffers the address of the realloc global offset table entry, and now when he sends a packet again, in this case, where create payload, this so here he's overflowing and is writing that GOT address, overriding the GOT address of the function realloc. And then he is sending data again, which now uses, now writes data over, actually, So this writes the address, and the next one is then using this address to write data there because it thinks that's the buffer, and then so it will overwrite the address in the global offset table. And then he sends another packet with a large ID that causes another reallocation of the array buffer. But now the the realloc function was overwritten, is pointing to another address, and it will crash. If you write it with AAs, it will crash segfault. You get it.
See.
Super straightforward exploit, right? If you can overwrite an address in the control structure in this array, you can point it anywhere and write data to it. So here's FFmpeg in GDB with the triggered segfault.
We are jumping directly to our Cs. We now have the control of the RIP register. We have successfully overwritten the got.plt section. Achieving code execution should be easy from now on. I hope that this video motivated you a little bit and shown that real-life exploitation may be rather simple, and this will encourage you to make your own research. Good luck.
This is a really great example. Thank you so much, Paul, for sharing this with us and all the work you have put into the recording. Make sure to follow him on Twitter and check the description for some links. And don't forget to check out the podcast episode with Paul if you haven't listened to it yet.
Crazy. So this was my least viewed technical video on the Live Overflow channel. Has almost 7,000 views. Here, give it some views. I don't think it wasn't too bad. I mean, of course, there are things that could be improved. The pacing could be improved, but that's something I still get wrong nowadays with the pseudo videos, especially as well. I still think it's a good video. So probably, maybe it wasn't the time yet, 2017 for a video like this. I feel like if I would release this video now, today, it would be a lot more popular, for sure. Yeah, so this is what you get because you are working on YouTube videos for years and years and years until your channel just slowly grows. Yeah, this was kind of very early. Cool.